By now, you've seen all of the main pieces of the recommender system algorithm, or the collaborative filtering algorithm. In this video, I want to just share one last implementational detail, namely mean normalization, which can sometimes just make the algorithm work a little bit better. To motivate the idea of mean normalization, let's consider an example of where there's a user that has not rated any movies. So in addition to our 4 users, Alice, Bob, Carol, and Dave, I've added a 5th user, Eve, who hasn't rated any movies. Let's see what our collaborative filtering algorithm will do on this user. Let's say that n is equal to 2, and so we're going to learn 2 features, and we're going to have to learn a parameter vector theta 5, which is going to be an R2. Remember, this is now vectors in Rn, not Rn plus 1. We're going to learn the parameter vector theta 5 for our user number 5, Eve. So if we look in the first term in this optimization objective, well, the user Eve hasn't rated any movies, and so there are no movies. There are no movies for which Rij is equal to 1 for the user Eve, and so this first term plays no role at all in determining theta 5 because there are no movies that Eve has rated. And so the only term that affects theta 5 is this term. And so we're saying that we want to choose vector theta 5 so that the last regularization term is as small as possible. In other words, we want to minimize this lambda over 2 theta 5 subscript 1 squared plus theta 5 subscript 2 squared. So that's the component of the regularization term that corresponds to user 5. And of course, if your goal is to minimize this term, then what you're going to end up with is just theta 5 equals 0, 0, because the regularization term is encouraging us to set parameters close to 0, and if there is no data to try to pull the parameters away from 0, because this first term it doesn't affect theta 5, we just end up with theta 5 equals the vector of our zeros. And so when we go to predict how user 5 will rate any movie, we have that theta 5 transpose xi for any I, that's just going to be equal to 0, right? So because theta 5 is 0, for any value of x, this inner product is going to be equal to 0. And what we're going to have, therefore, is that we're going to predict that Eve is going to rate every single movie with 0 stars. But this doesn't seem very useful, does it? I mean, if you look at the different movies, Love at Last, this first movie, a couple people rated it 5 stars, and for even the Swords versus Karate, someone rated it 5 stars. So some people do like some movies. It seems kind of not useful to just predict that Eve is going to rate everything 0 stars. And in fact, if we're predicting that Eve is going to rate everything 0 stars, we also don't have any good way of recommending any movies to her, because all of these movies are getting exactly the same predicted rating for Eve, so there's no one movie with a higher predicted rating that we could recommend to her. So that's not very good. The idea of mean normalization will let us fix this problem. So here's how it works. As before, let me group all of my movie ratings into this matrix Y. So just take all of these ratings and group them into this matrix Y. And this column over here of all question marks corresponds to Eve's not having rated any movies. Now, to perform mean normalization, what I'm going to do is compute the average rating that each movie obtained. And I'm going to store that in a vector that we call mu. So the first movie got 2 5-star and 2 0-star ratings, so the average of that is a 2.5 star rating. The second movie had an average of 2.5 star, and so on. Then the final movie has 0050, and the average of 0050, that averages out to an average of 1.25 rating. And then what I'm going to do is look at all the movie ratings, and I'm going to subtract off the mean ratings. So this first element 5, I'm going to subtract off a 2.5, and that gives me a 2.5. And the second element 5, subtract off a 2.5, get a 2.5. And then these 0 zeros, subtract off 2.5, and we get minus 2.5, minus 2.5. In other words, what I'm going to do is take my matrix of movie ratings, take this Y matrix, and subtract from each row the average rating for that movie. So what I'm doing is I'm just normalizing each movie to have an average rating of 0. And so just one last example, if you look at this last row, the 0050, I'm going to subtract 1.25, and so I end up with these values over here. Okay, so now, and of course the question marks stay a question mark. And so each movie in this new matrix Y has an average rating of 0. What I'm going to do then is take this set of ratings and use it with my collaborative filtering algorithm. So I'm going to pretend that this was the data that I had gotten from my users. I'm going to pretend that these were the actual ratings I had gotten from the users, and I'm going to use this as my data set with which to learn my parameters theta j and my features xi from these mean normalized movie ratings. When I want to make predictions of movie ratings, what I'm going to do is the following. For a user j on movie I, I'm going to predict theta j transpose xi, where x and theta are the parameters I've learned from this mean normalized data set. But because on the data set I had subtracted off the means, in order to make a prediction on movie I, I'm going to need to add back in the mean, and so I'm going to add back in mu I. And so that's going to be my prediction, where in my training data I subtracted off all the means, and so when I make predictions I need to add back in these means mu I for movie I. And so specifically for user 5, which is Eve, the same argument as the previous slide still applies, in the sense that Eve had not rated any movies, and so the learn parameter for user 5 is still going to be equal to 0, 0. So what we're going to get then is that on a particular movie I, we're going to predict for Eve theta 5 transpose xi plus add back in mu I. And so this first component is going to be equal to 0 if theta 5 is equal to 0. And so on movie I, we're going to end up predicting mu I. And this actually makes sense. It means that on movie 1, we're going to predict Eve rates at 2.5. On movie 2, we're going to predict Eve rates at 2.5. On movie 3, we're going to predict Eve rates at 2, and so on. And this actually makes sense because it says that if Eve hasn't rated any movies, we just don't know anything about this new user Eve, what we're going to do is just predict for each of the movies whatever the average rating that those movies got. Finally, as an aside, in this video we talked about mean normalization, where we normalize each row of the matrix Y to have mean 0. In case you have some movies with no rating, so this is analogous to a user who hasn't rated anything, but in case you have some movies with no ratings, you can also play with versions of the algorithm where you normalize the different columns to have mean 0 instead of normalizing the rows to have mean 0, although that's maybe less important because if you really have a movie with no ratings, maybe you just shouldn't recommend that movie to anyone anyway. And so taking care of the case of a user who hasn't rated anything might be more important than taking care of the case of a movie that hasn't gotten a single rating. So to summarize, that's how you can do mean normalization as a sort of pre-processing step for collaborative filtering. Depending on your data set, this might sometimes make your implementation work just a little bit better. In the next few videos, we'll talk about large-scale machine learning. That is, algorithms for dealing with big data sets. If you look back at the recent 5 or 10-year history of machine learning, one of the reasons that learning algorithms work so much better now than even, say, 5 years ago is just the sheer amount of data that we have now and that we can train our algorithms on. In these next few videos, we'll talk about algorithms for dealing with when we have such massive data sets. So why do we want to use such large data sets? We've already seen that one of the best ways to get a high-performance machine learning system is if you take a low-bias learning algorithm and train that on a lot of data. And so one early example that we've already seen was this example of classifying between confusable words. So for breakfast, I ate 2 TWO eggs. And we saw in this example these sorts of results where, so long as you feed the algorithm a lot of data, it seems to do very well. And so it's results like these that has led to the saying in machine learning that often is not who has the best algorithm that wins, is who has the most data. So we want to learn from large data sets, at least when we can get such large data sets. But learning with large datasets comes with its own unique problems, specifically computational problems. Let's say your training set size is m equals 100 million. And this is actually pretty realistic for many modern data sets. If you look at the US Census data set, if there are 300 million people in the US, you can easily get hundreds of millions of records. If you look at the amount of traffic that popular websites get, you easily get training sets that are much larger than hundreds of millions of examples. And let's say you want to train a linear regression model or maybe a logistic regression model, in which case this is the gradient descent rule. And if you look at what you need to do to compute the gradient, which is this term over here, then when m is 100 million, you need to carry out a summation over 100 million terms in order to compute this derivative term and to perform a single step of gradient descent. Because of the computational expense of summing over 100 million entries in order to compute just one step of gradient descent, in the next few videos we'll talk about techniques for either replacing this algorithm with something else or to find more efficient ways to compute this derivative. By the end of the sequence of videos on large-scale machine learning, you know how to fit models, linear regression, logistic regression, neural networks, and so on, even to data sets with, say, 100 million examples. Of course, before we put in the effort into training a model with 100 million examples, we should also ask ourselves, well, why not use just 1,000 examples? Maybe we can randomly pick a subset of 1,000 examples out of 100 million examples and train our algorithm on just 1,000 examples. So before investing the effort into actually developing the software needed to train these massive models, it's often good to sanity check if training on just 1,000 examples might do just as well. The way to sanity check if using a much smaller training set might do just as well, that is, if using a much smaller m equals 1,000 size training set might do just as well, is the usual method of plotting the learning curves. So if you were to plot the learning curves, and if your training objective were to look like this, that's j train theta, and if your cross-validation set objective JCV of theta were to look like this, then this looks like a high variance learning algorithm, and we would be more confident that adding extra training examples would improve performance. Whereas in contrast, if you were to plot the learning curves, if your training objective were to look like this, and if your cross-validation objective were to look like that, then this looks like the classical high bias learning algorithm. And in the latter case, if you were to plot this up to, say, m equals 1,000, right, so that's m equals 500 up to m equals 1,000, then it seems unlikely that increasing m to 100 million will do much better, and then you'd be just fine sticking to m equals 1,000 rather than investing a lot of effort to figure out how to scale up the algorithm. Of course, if you were in the situation shown by the figure on the right, then one natural thing to do would be to add extra features or add extra hidden units to your neural network and so on, so that you end up at a situation closer to that on the left, where maybe this is up to m equals 1,000, and this then gives you more confidence that trying to add infrastructure or change the algorithm to use much more than 1,000 examples, that might actually be a good use of your time. So in large-scale machine learning, we'd like to come up with computationally reasonable ways or computationally efficient ways to deal with very big data sets. In the next few videos, we'll see two main ideas. The first is called stochastic gradient descent, and the second is called MapReduce for dealing with very big data sets. And after you've learned about these methods, hopefully that will allow you to scale up your learning algorithms to big data and allow you to get much better performance on many different applications. For many learning algorithms, among them linear regression, logistic regression, and neural networks, the way we derived the algorithm was by coming up with a cost function or coming up with an optimization objective, and then using an algorithm like gradient descent to minimize that cost function. When you have a very large training set, gradient descent becomes a computationally very expensive procedure. In this video, we'll talk about a modification to the basic gradient descent algorithm called stochastic gradient descent, which will allow us to scale these algorithms to much bigger training sets. Suppose you are training a linear regression model using gradient descent. As a quick recap, the hypothesis will look like this, and the cost function will look like this, which is this sort of 1/2 of the average squared error of your hypothesis on your M training examples. And the cost function, we've already seen, looks like this sort of bowl-shaped function. So plotted as a function of the parameters theta 0 and theta 1, the cost function j is a sort of a bowl-shaped function. And gradient descent looks like this, where in the inner loop of gradient descent, you repeatedly update the parameters theta using that expression. Now, in the rest of this video, I'm going to keep using linear regression as the running example, but the idea is here, the idea of stochastic gradient descent is fully general and also applies to other learning algorithms like logistic regression, neural networks, and other algorithms that are based on training gradient descent on a specific training set. So here's a picture of what gradient descent does. If the parameters are initialized at a point there, then as you run gradient descent, different iterations of gradient descent will take the parameters to the global minimum. So take a trajectory that looks like that and heads pretty directly to the global minimum. Now the problem with gradient descent is that if m is large, then computing this derivative term can be very expensive because this requires summing over all m examples. So if m is 300 million, right, so in the United States there are about 300 million people, and so the US or United States census data may have on the order of that many records. So if you want to fit the linear regression model to that, then you need to sum over 300 million records, and that's very expensive. To give the algorithm a name, this particular version of gradient descent is also called batch gradient descent. And the term batch refers to the fact that we're looking at all of the training examples at a time. We call it sort of a batch of all of the training examples. It really isn't maybe the best name, but this is what machine learning people call this particular version of gradient descent. And if you imagine really that you have 300 million census records stored away on disk, the way this algorithm works is you would need to read into your computer memory all 300 million records in order to compute this derivative term. You need to stream all of these records through computer because you can't store all your records in computer memory. So you need to read through them and slowly, accumulate the sum in order to compute the derivative. And then having done all that work, that allows you to take one step of gradient descent. And now you need to do the whole thing again. Scan through all 300 million records, accumulate these sums, and having done all that work, you can take another little step using gradient descent, and then do that again, and then as you take yet a third step, and so on. And so this can take a long time in order to get the algorithm to converge. In contrast to batch gradient descent, what we're going to do is come up with a different algorithm that doesn't need to look at all of the training examples in every single iteration, but that needs to look at only a single training example in one iteration. Before moving on to the new algorithm, here's just the batch gradient descent algorithm written on the game, with that being the cost function and that being the update. And of course, this term here that's used in the gradient descent rule, that is the partial derivative with respect to the parameter theta j of our optimization objective, j train of theta. Now let's look at the more efficient algorithm that scales better to large data sets. In order to work out the algorithm, it's called stochastic gradient descent, let's write out the cost function in a slightly different way. We're going to define the cost of a parameter theta with respect to a training example xi comma yi to be equal to 1/2 times the squared error that my hypothesis incurs on that example xi comma yi. So this cost function term really measures how well is my hypothesis doing on a single example xi comma yi. Now you notice that the overall cost function j train can now be written in this equivalent form. So j train is just the average over my m training examples of the cost of my hypothesis on that example xi comma yi. Armed with this view of the cost function for linear regression, let me now write out what stochastic gradient descent does. The first step of stochastic gradient descent is to randomly shuffle the data set. So by that I just mean randomly shuffle or randomly reorder your M training examples. It's sort of a standard pre-processing step. Come back to this in a minute. But the main work of stochastic gradient descent is then done in the following. We're going to repeat for I equals 1 through m. So I'm going to repeatedly scan through my training examples and perform the following update. I'm going to update the parameter theta j as theta j minus alpha times h of xi minus yi times xi j. And we're going to do this update as usual for all values of j. Now, you notice that this term over here is exactly what we had inside the summation for Bash gradient descent. In fact, for those of you that are familiar with calculus, it's possible to show that that term here, this term here, is equal to the partial derivative with respect to my parameter theta j of the cos of the parameters theta on xi comma yi, where cos is of course this thing that was defined previously. And just to wrap up the algorithm, let me close my curly braces over there. Okay. So what stochastic gradient descent is doing is actually scanning through the training examples, and first it's going to look at my first training example x1 comma y1. And then looking at only this first example, it's going to take like basically a little gradient descent step with respect to the cost of just this first training example. So in other words, it's going to look at the first example and modify the parameters a little bit to fit just the first training example a little bit better. Having done this, inside this inner for loop is then going to go on to the second training example. And what it's going to do there is take another little step in parameter space, so modify the parameters just a little bit to try to fit just the second training example a little bit better. Having done that, is then going to go on to my third training example and modify the parameters to try to fit just the third training example a little bit better, and so on until it gets through the entire training set. And then this outer repeat loop may cause it to take multiple passes over the entire training set. This view of stochastic gradient descent also motivates why we wanted to start by randomly shuffling the dataset. This just ensures that when we scan through the training set here, that we end up visiting the training examples in some sort of randomly sorted order. Depending on whether your data already came randomly sorted or whether it came originally sorted in some strange order, in practice this could just speed up the convergence of stochastic gradient descent just a little bit. So in the interest of safety, it's usually better to randomly shuffle the dataset if you're unsure if it came to you in randomly sorted order or not. But more importantly, another view of stochastic gradient descent is that it's a lot like Bash gradient descent. But rather than waiting to sum up these gradient terms over all m training examples, what we're doing is we're taking this gradient term using just one single training example, and we're starting to make progress in improving the parameters already. So rather than waiting till we've taken a pass through all 300,000 United States Census records, say, rather than needing to scan through all of the training examples before we can modify the parameters a little bit and make progress towards the global minimum. For stochastic gradient descent, instead, we just need to look at a single training example and we'll already start making progress in the space of parameters towards moving the parameters towards the global minimum. So here's the algorithm written out again, where the first step is to randomly shuffle the data, and the second step is where the real work is done, where that's the update with respect to a single training example xi comma yi. So let's see what this algorithm does to the parameters. Previously, we saw that when we're using Bash gradient descent, that is the algorithm that looks at all the training examples at the time, Bash gradient descent would tend to take a reasonably straight line trajectory to get to the global minimum like that. In contrast, with stochastic gradient descent, every iteration is going to be much faster because we don't need to sum up over all the training examples, but every iteration is just trying to fit a single training example better. So if we were to start stochastic gradient descent, let's start stochastic gradient descent at a point like that. The first iteration, may take the parameters in that direction. And maybe the second iteration, looking at just the second example, maybe just by chance we get a little unlucky and actually head in a bad direction and move the parameters like that. In the third iteration, where we try to modify the parameters to fit just the third training examples better, maybe we'll end up heading in that direction. And then we look at the fourth training example, maybe we'll do that, the fifth example, sixth example, seventh, and so on. And as you run stochastic gradient descent, what you find is that it will generally move the parameters in the direction of the global minimum, but not always. And so take a somewhat more random looking and circuitous path towards the global minimum. And in fact, as you run stochastic gradient descent, it doesn't actually converge in the same sense as batch gradient descent does. And what it ends up doing is wandering around continuously in some region close to the global minimum, but it doesn't actually just get to the global minimum and stay there. But in practice, this isn't a problem because, so long as the parameters end up in some region there, maybe it's pretty close to the global minimum, so long as the parameters end up pretty close to the global minimum, that will be a pretty good hypothesis. And so usually running stochastic gradient descent, we get a parameter near the global minimum, and that's good enough for almost essentially most practical purposes. Just one final detail, in stochastic gradient descent we had this outer loop repeat which says to do this inner loop multiple times. So how many times do we repeat this outer loop? Depending on the size of the training set, doing this loop just a single time may be enough, and up to maybe 10 times may be typical. So you may end up repeating this inner loop anywhere from once to 10 times. So if you have a truly massive data set like this US Census dataset example that I've been talking about with 300 million examples, it's possible that by the time you've taken just a single pass through your training set, so this is for I equals 1 through 300 million, it's possible that by the time you've taken a single pass through your dataset, you might already have a perfectly good hypothesis, in which case, this inner loop you might need to do only once if M is very, very large. But in general, taking anywhere from 1 through 10 passes through your data set, may be fairly common, but really it depends on the size of your training set. And if you contrast this to batch gradient descent, with batch gradient descent, after taking a pass through your entire training set, you would have taken just one single gradient descent step. So one of these little baby steps of gradient descent where you just take one small gradient descent step. And this is why stochastic gradient descent can be much faster. So that was the stochastic gradient descent algorithm, and if you implement it, hopefully that will allow you to scale up many of your learning algorithms to much bigger data sets and get much better performance that way. In the previous video, we talked about stochastic gradient descent and how that can be much faster than batch gradient descent. In this video, let's talk about another variation on these ideas called mini batch gradient descent that can work sometimes even a bit faster than stochastic gradient descent. To summarize the algorithms we've talked about so far, in batch gradient descent, we would use all m examples in each iteration, whereas in stochastic gradient descent, we would use a single example in each iteration. What mini batch gradient descent does is somewhere in between. Specifically, with this algorithm, we're going to use b examples in each iteration, where b is a parameter called the mini batch size. So the idea is that this is somewhere in between batch gradient descent and stochastic gradient descent, and it's just like batch gradient descent, except that we're going to use a much smaller batch size. A typical choice for the value of b might be b equals 10, let's say, and a typical range really might be anywhere from b equals 2 up to b equals 100. So that would be a pretty typical range of values for the mini batch size. And the idea is that rather than using one example at a time or m examples at a time, we're going to use b examples at a time. So let me just write this out informally. We're going to get, let's say, b, for this example, let's say b equals 10. So we're going to get the next 10 examples from our training set. So that may be some set of examples, xi, yi. If it's 10 examples, then the indexing would be up to xi plus 9, comma, yi plus 9, so that's 10 examples altogether, and then we'll perform essentially a gradient descent update using these 10 examples. So that's learning rate times 1/10 times sum over k equals I through I plus 9 of h subscript theta of xk minus yk times x kj. And so in this expression, we're summing the gradient terms over my 10 examples. So there's a number 10, that's my mini batch size, and this I plus 9, again the 9 comes from the choice of the parameter b. And then after this, we will then increase I by 10, so go on to the next 10 examples, and then keep looping like this. So just to write out the entire algorithm in full, in order to simplify the indexing for this, for what I'm going to write out, I'm going to assume we have a mini batch size of 10 and a training set size of 1,000. What we're going to do is have this sort of for loop, for I equals 1, 11, 21, so stepping in steps of 10, because we look at 10 examples at a time. And then we perform this sort of gradient descent update using 10 examples at a time. So this 10 and this I plus 9, those are a consequence of having chosen my mini batch size to be 10, and this outermost for loop, this ends at 991 here, because if I have 1,000 training examples, then I need 100 steps of size 10 in order to get through my entire training set. So this is mini batch gradient descent. Compared to batch gradient descent, this also allows us to make progress much faster. So we have, again, our running example of US Census data with 300 million training examples. Then what we're saying is, after looking at just the first 10 examples, we can start to make progress in improving the parameters data. So we don't need to scan through the entire training set. We just need to look at the first 10 examples, and this will start letting us make progress. And then we can look at the second 10 examples and modify the parameters a little bit again, and so on. So that's why mini batch gradient descent can be faster than batch gradient descent. Namely, you can start making progress in modifying the parameters after looking at just 10 examples, rather than needing to wait till you've scanned through every single training example, or 300 million of them. So how about mini batch gradient descent versus stochastic gradient descent? So why do we want to look at b examples at a time, rather than look at just a single example at a time, as in stochastic gradient descent? The answer is in vectorization. In particular, mini batch gradient descent is likely to outperform stochastic gradient descent only if you have a good vectorized implementation. In that case, this sum over 10 examples can be performed in a more vectorized way, which will allow you to partially parallelize your computation over the 10 examples. So in other words, by using appropriate vectorization to compute the derivative terms, you can sometimes partially use the good numerical linear algebra libraries to parallelize your gradient computations over the b examples. Whereas if you were looking at just a single example at a time with stochastic gradient descent, then looking at just one example at a time, there isn't much to parallelize over, or at least there's less to parallelize over. One disadvantage of mini batch gradient descent is that there's now this extra parameter b, the mini batch size, which you may have to fiddle with and which may therefore take time. But if you have a good vectorized implementation, this can sometimes run even faster than stochastic gradient descent. So that was mini batch gradient descent, which is an algorithm that in some sense does something that's somewhere in between what stochastic gradient descent does and what batch gradient descent does. And if you choose a reasonable value of b, I usually use b equals 10, but other values anywhere from say 2 to 100 would be reasonably common. So if you choose a good value of b, and if you use a good vectorized implementation, sometimes it can be faster than both stochastic gradient descent and faster than batch gradient descent. You now know about the stochastic gradient descent algorithm, but when you're running the algorithm, how do you make sure that it is sort of completely debugged and that it's converging okay? And equally important, how do you tune the learning rate alpha for stochastic gradient descent? In this video, we'll talk about some techniques for doing these things, for making sure it's converging, and for picking the learning rate alpha. Back when we were using batch gradient descent, our standard way for making sure that gradient descent was converging was we would plot the optimization cost function as a function of the number of iterations. So that was the cost function, and we would make sure that this cost function is decreasing on every iteration. When the training set size was small, we could do that because we could compute this sum pretty efficiently, but when you have a massive training set size, then you don't want to have to pause your algorithm periodically. You don't want to have to pause stochastic gradient descent periodically in order to compute this cost function, since it requires a sum over your entire training set size. And the whole point of stochastic gradient descent was that you wanted to start to make progress after looking at just a single example without needing to occasionally scan through your entire training set right in the middle of the algorithm just to compute things like the cost function over your entire training set. So for stochastic gradient descent, in order to check that the algorithm is converging, here's what we can do instead. Let's take the definition of the cost that we had previously. So the cost of the parameters theta with respect to a single training example is just 1/2 of the square error on that training example. Then while stochastic gradient descent is learning, right before we train on a specific example, so in stochastic gradient descent, we're going to look at the examples xi, yi in order, and then sort of take a little update with respect to this example, and then go on to the next example, xi plus 1, yi plus 1, and so on, right? That's what stochastic gradient descent does. So while the algorithm is looking at the example xi, yi, but before it has updated the parameters theta using that example, let's compute the cost of that example. Just to say the same thing again, but using slightly different words, as stochastic gradient descent is scanning through our training set, right before we have updated theta using a particular training example xi, yi, let's compute how well our hypothesis is doing on that training example. Okay, and we want to do this before updating theta, because if we've just updated theta using that training example, then it might be doing better on that example than would be representative. Finally, in order to check for the convergence of stochastic gradient descent, what we can do is every 1,000 iterations, we can plot these costs that we've been computing in the previous step. We can plot those costs average over, say, the last 1,000 examples processed by the algorithm. And if you do this, it kind of gives you a running estimate of how well the algorithm is doing on, the last 1,000 training examples that your algorithm has seen. So in contrast to computing JTrain periodically, which needed to scan through the entire training set, with this sort of procedure, well, as part of stochastic gradient descent, it doesn't cost much to compute these costs as well right before updating the parameter theta. And all we're doing is every 1,000 iterations or so, we just average the last 1,000 costs that we computed and we plot that. And by looking at those plots, this will allow us to check if stochastic gradient descent is converging. So here are a few examples of what these plots might look like. Suppose we were to plot the cost average over the last 1,000 examples. Because these are average over just 1,000 examples, they are going to be a little bit noisy, and so it may not decrease on every single iteration. But if you get a figure that looks like this, so the plot is noisy because it's average over just a small subset, say 1,000 training examples. If you get a figure that looks like this, that would be a pretty decent run of the algorithm maybe, where it looks like the cost has gone down and then it's plateaued out, it's kind of flattened out, starting from around that point. So it looks like if this is what your cost looks like, then maybe your learning algorithm has converged. If you were to try using a smaller learning rate, something that you might see is that the algorithm may initially learn more slowly, so the cost goes down more slowly, but then eventually with a smaller learning rate, it's actually possible for the algorithm to end up at a maybe very slightly better solution. So the red line may represent the behavior of stochastic gradient descent using a smaller learning rate. And the reason this is the case is because you remember stochastic gradient descent doesn't just converge to the global minimum. Instead, what it does is the parameters will oscillate a bit around the global minimum. And so by using a smaller learning rate, you end up with smaller oscillations. And sometimes this little difference will be negligible. And sometimes with a smaller learning rate, you can get a slightly better value for the parameters. Here are some other things that might happen. Let's say you run stochastic gradient descent and you average over 1,000 examples when plotting these costs. So here might be a result of another one of these plots, and again it kind of looks like it's converged. If you were to take this number 1,000 and increase it to averaging over 5,000 examples, then it's possible that you might get a smoother curve that looks more like this. And by averaging over, say, 5,000 examples instead of 1,000, you might be able to get a smoother curve like this. And so that's the effect of increasing the number of examples you average over. The disadvantage of making this too big, of course, is that now you get one data point only every 5,000 examples. And so the feedback you get on how well your learning algorithm is doing is sort of, maybe it's more delayed, because you get one data point on your plot only every 5,000 examples rather than every 1,000 examples. Along a similar vein, sometimes you may run stochastic gradient descent and end up with a plot that looks like this. And with a plot that looks like this, you know, it looks like the cost just is not decreasing at all. It looks like the algorithm is just not learning. It just looks like basically a flat curve, and it's just the cost is just not decreasing. But again, if you were to increase this to averaging over a larger number of examples, it's possible that you see something like this red line. It looks like the cost actually is decreasing. It's just that the blue line, averaging over too few examples, the blue line was too noisy, so you couldn't see the actual trend in the cost actually decreasing. And possibly averaging over 5,000 examples instead of 1,000 may help. Of course, when you average over a larger number of examples, if you were to average over 5,000 examples, I'm just using a different color, it's also possible that you see that the learning curve ends up looking like this. That it's still flat even when you're averaging over a larger number of examples. And if you get that, then that's maybe just a more firm verification that unfortunately the algorithm just isn't learning much for whatever reason, and you need to either change the learning rate or change the features or change something else about the algorithm. Finally, one last thing that you might see would be if you were to plot these curves and you see a curve that looks like this, where it actually looks like it's increasing. And if that's the case, then this is a sign that the algorithm is diverging. And what you really should do is use a smaller value of the learning rate alpha. So hopefully this gives you a sense of the range of phenomena you might see when you plot these costs average over some range of examples, as well as suggest the sorts of things you might try to do in response to seeing different plots. So if the plot looks too noisy, if it sort of wiggles up and down too much, then try increasing the number of examples you're averaging over so that you can see the overall trend in the plot better. And if you see that the errors are actually increasing, the costs are actually increasing, try using a smaller value of alpha. Finally, it's worth examining the issue of the learning rate just a little bit more. We saw that when we run stochastic gradient descent, the algorithm will start here and sort of meander towards the minimum, and then it won't really converge, but instead it'll wander around the minimum forever. And so you end up with a parameter value that is hopefully close to the global minimum, but won't be exactly at the global minimum. In most typical implementations of stochastic gradient descent, the learning rate alpha is typically held constant, and so what you typically end up with is exactly a picture like this. If you want stochastic gradient descent to actually converge to the global minimum, there's one thing which you can do, which is you can slowly decrease the learning rate alpha over time. So a pretty typical way of doing that would be to set alpha equals some constant 1 divided by iteration number plus constant 2. So iteration number is the number of iterations you've run of stochastic gradient descent, so it's really the number of training examples you've seen, and const 1 and const 2 are additional parameters of the algorithm that you might have to play with a bit in order to get good performance. One of the reasons people tend not to do this is because you end up needing to spend time playing with these two extra parameters, const 1 and const 2. And so this makes the algorithm more finicky. It's just more parameters that you need to fiddle with in order to make the algorithm work well. But if you manage to tune the parameters well, then the picture you can get is that the algorithm will actually meander around towards the minimum, but as it gets closer, because you're decreasing the learning rate, the meanderings will get smaller and smaller until it pretty much just converges to the global minimum. I hope this makes sense, right? And the reason this formula makes sense is because as the algorithm runs, the iteration number becomes large, and so alpha will slowly become small, and so you take smaller and smaller steps until it sort of, hopefully converges to the global minimum. So if you do slowly decrease alpha to 0, you can end up with a slightly better hypothesis but because of the extra work needed to fill up the constants, and because frankly usually we're pretty happy with any parameter value that's pretty close to global minimum, typically this process of decreasing alpha slowly is usually not done, and keeping the learning rate alpha constant is the more common application of stochastic gradient descent, although you will see people use either version. To summarize, in this video we talked about a way for approximately monitoring how stochastic gradient descent is doing in terms of optimizing the cost function. And this is a method that does not require scanning over the entire training set periodically to compute the cost function on the entire training set. But instead it looks at, say, only the last 1,000 examples or so. And you can use this method both to make sure that stochastic gradient descent is running okay and is converging, or to use it to tune the learning rate alpha. In this video, I'd like to talk about a new large-scale machine learning setting called the online learning setting. The online learning setting allows us to model problems where we have a continuous flood or a continuous stream of data coming in, and we would like an algorithm to learn from that. Today, many of the largest websites or many of the largest website companies use different versions of online learning algorithms to learn from the flood of users that keep on coming back to the website. Specifically, if you have a continuous stream of data generated by a continuous stream of users coming to your website, what you can do is sometimes use an online learning algorithm to learn user preferences from the stream of data and use that to optimize some of the decisions on your website. Suppose you run a shipping service, so users come and ask you to help ship their packages from location A to location B. And suppose you run a website where users repeatedly come and they tell you where they want to send the package from and where they want to send it to, so the origin and destination, and your website offers to ship the package for some asking price. So I'll ship your package for $50, I'll ship it for $20. And based on the price that you offer to the users sometimes choose to use a shipping service. That's a positive example. And sometimes they go away and they do not choose to purchase your shipping service. So let's say that we want a learning algorithm to help us to optimize what is the asking price that we want to offer to our users. And specifically, let's say we come up with some set of features that capture properties of the users, if we know anything about the demographics. They capture the origin and destination of the package, where they want to ship the package, and what is the price that we offer to them for shipping the package. And what we want to do is learn what is the probability that they will elect to ship the package using our shipping service given these features. And again, just as a reminder, these features X also captures the price that we're asking for. And so if we could estimate the chance that they'll agree to use our service for any given price, then we can try to pick a price so that they have a pretty high probability of choosing our website, while simultaneously hopefully offering us a fair return, offering us a fair profit for shipping their package. So if we can learn this probability of y equals 1 given any price and given the other features, we can really use this to choose appropriate prices as new users come to us. So in order to model the probability of y equals 1, what we can do is use logistic regression or a neural network or some other algorithm like that. But let's start with logistic regression. Now, if you have a website that just runs continuously, here's what an online learning algorithm would do. I'm going to write repeat forever. This just means that our website is going to keep on staying up. And what happens on the website is occasionally a user will come, and for the user that comes, we'll get some XY pair, right, corresponding to a customer or to a user on the website. So the features X are the origin and destination specified by this user and the price that we happen to offer to them this time around, and Y is either 1 or 0 depending on whether or not they chose to use our shipping service. Now once we get this XY pair, what an online learning algorithm does is then update the parameters data using just this example X comma Y. And in particular, we will update my parameters data as data J gets updated as theta j minus the learning rate alpha times my usual gradient descent rule for logistic regression. So we do this for j equals 0 up to n, and that's my closed curly brace. So for other learning algorithms, instead of writing xy, right, I was writing things like xi, comma yi. But in this online learning setting, we're actually discarding the notion of there being a fixed training set. Instead, we have an algorithm. And what happens is we get an example, and then we learn using that example like so, and then we throw that example away. We discard that example, and we never use it again. And so that's why we just look at one example at a time, and we learn from that example, we discard it, which is why we're also doing away with this notion of there being this sort of fixed training set indexed by I. And if you really run a major website where you really have a continuous stream of users coming, then this sort of online learning algorithm is actually a pretty reasonable algorithm. Because if data is essentially free, if you have so much data, that data is essentially unlimited, then there's really maybe no need to look at a training example more than once. Of course, if you had only a small number of users, then rather than using an online learning algorithm like this, you might be better off saving away all your data in a fixed training set and then running some algorithm over that training set. But if you really have a continuous stream of data, then an online learning algorithm can be very effective. I should mention also that one interesting effect of this sort of online learning algorithm is that it can adapt to changing user preferences. And in particular, if over time, because of changes in the economy, maybe users start to become more price sensitive and willing to pay, less willing to pay high prices, or become less price sensitive and they're willing to pay higher prices, or if different things become more important to users, if you start to have new types of users coming to your website, this sort of online learning algorithm can also adapt to changing user preferences and kind of keep track of what your changing population of users may be willing to pay for. And it does that because if your pool of users changes, then these updates to your parameters data will just slowly adapt your parameters to whatever your latest pool of users looks like. Here's another example of a sort of application to which you might apply online learning. This is an application in product search in which we want to apply a learning algorithm to learn to give good search listings to a user. Let's say you run an online store that sells phones, that sells mobile phones or sells cell phones, and you have a user interface where a user can come to your website and type in the query like Android phone 1080p camera. So 1080p is a type of a specification for a video camera that you might have in a phone, in a cell phone or mobile phone. Suppose we have 100 phones in our store, and because of the way our website is laid out, when a user types in the query for the search query, we would like to find a choice of 10 different phones to show or to offer to the user. What we'd like to do is have a learning algorithm help us to figure out what are the 10 phones out of the 100 we should return to a user in response to a user search query like the one here. Here's how we can go about the problem. For each phone, and given a specific user query, we can construct a feature vector X. So the feature vector X might capture different properties of the phone. It might capture things like how similar the user search query is to the phone. So we capture things like how many words in the user search query match the name of the phone, how many words in the user search query match the description of the phone, and so on. So the features X capture properties of the phone, and it captures things about how similar or how well the phone matches the user query along different dimensions. What we'd like to do is estimate the probability that a user will click on the link for a specific phone, because we want to show the user phones that they're likely to want to buy. We want to show the user phones that they have a high probability of clicking on in their web browser. So I'm going to define y equals 1 if a user clicks on a link for a phone, and y equals 0 otherwise. And what I would like to do is learn the probability that a user will click on a specific phone given the features X, which capture properties of the phone, and how well the query matches the phone. To give this problem a name, in the language of people that run websites like this, the problem of learning this is actually called the problem of learning the predicted click-through rate, or predicted CTR. It just means learning the probability that the user will click on the specific link that you offer them. So CTR is an abbreviation for click-through rate. And if you can estimate the predicted click-through rate for any particular phone, what we can do is use this to show the user the 10 phones that they're most likely to click on. Because out of the 100 phones, we can compute this for each of the 100 phones and just select the 10 phones that the user is most likely to click on. And this would be a pretty reasonable way to decide what 10 results to show to the user. Just be clear, right? Suppose that every time a user does a search, we return 10 results. What that will do is it will actually give us 10 XY pairs. So this actually gives us 10 training examples every time a user comes to our website, because for the 10 phones that we chose to show the user, for each of those 10 phones we get a feature vector X, and for each of those 10 phones we show the user, we will also get a value for Y. We will also observe a value of Y depending on whether or not they clicked on that URL or not. And so one way to run a website like this would be to continuously show the user, your 10 best guesses for what are the phones they might like. And so each time a user comes, you would get 10 examples, 10 XY pairs, and then use an online learning algorithm to update the parameters using essentially 10 steps of gradient descent on these 10 examples. And then you can throw the data away. And if you really have a continuous stream of users coming to your website, this would be a pretty reasonable way to learn parameters for your algorithm so as to show the 10 phones to your users that are maybe most promising and that they're most likely to click on. So this is a product search problem, or learning to rank phones, or learning to search for phones example. So I'll quickly mention a few others. One is if you have a website, you're trying to decide what special offers to show the user. This is very similar to phones. Or if you have a website and you show different users different news articles. So if you're a news aggregator website, then you can again use a similar system to show to the user, what are the news articles that they are most likely to be interested in, and what are the news articles that they're most likely to click on. Closely related to special offers would be product recommendations. And in fact, if you have a collaborative filtering system, you can even imagine a collaborative filtering system giving you additional features to feed into a logistic regression classifier to try to predict the click-through rate for different products that you might recommend to a user. Of course, I should say that any of these problems could also have been formulated as a standard machine learning problem where you have a fixed training set. Maybe you can run your website for a few days and then save away a fixed training set, and run a learning algorithm on that. But these are the actual sorts of problems where you do see large companies get so much data that there's really maybe no need to save away a fixed training set, but instead you can use an online learning algorithm to just learn continuously from the data that users are generating on your website. So that was the online learning setting, and as we saw, the algorithm that we applied to it is really very similar to the stochastic gradient descent algorithm, only instead of scanning through a fixed training set, we're instead getting one example from the users, learning from that example, then discarding it and moving on. And if you have a continuous stream of data for some application, this sort of algorithm may be well worth considering for your application. And of course, one other advantage of online learning is also that if you have a changing pool of users, or if the things you're trying to predict are slowly changing, like if your user taste is slowly changing, the online learning algorithm can slowly adapt your learned hypothesis to whatever the latest sets of user behaviors are like as well. In the last few videos, we talked about stochastic gradient descent and other variations of the stochastic gradient descent algorithm, including its adaptation to online learning. But all of those algorithms could be run on one machine, or could be run on one computer. And some machine learning problems are just too big to run on one machine. And sometimes maybe you just have so much data, you just don't ever want to run all that data through a single computer, no matter what algorithm you want to use on that computer. So in this video, I'd like to talk about a different approach to large-scale machine learning called the MapReduce approach. And even though we had quite a few videos on stochastic gradient descent and going to spend relatively less time on MapReduce, don't judge the relative importance of MapReduce versus stochastic gradient descent based on the amount of time I spend on these ideas. In particular, many people will say that MapReduce is at least an equally important, and some will say an even more important idea compared to stochastic gradient descent. only it is relatively simpler to explain, which is why I'm going to spend less time on it. But using these ideas, you might be able to scale learning algorithms to even far larger problems than is possible using stochastic gradient descent. Here's the idea. Let's say we want to fit a linear regression model or logistic regression model or some such, and let's start again with Bash gradient descent. So that's our Bash gradient descent learning rule. And to keep the writing on this slide tractable, I'm going to assume throughout that we have m equals 400 examples. Of course, by our standards, in terms of large-scale machine learning, m might be pretty small, and so this might be more commonly applied to problems where you have maybe closer to 400 million examples or some such. But just to make the writing on this slide simpler, I'm going to pretend we have 400 examples. So in that case, the Bash gradient descent learning rule has this 1 over 400, and this sum from I equals 1 through 400 through my 400 examples here. And if m is large, then this is a computationally expensive step. So what the MapReduce idea does is the following. And I should say the MapReduce idea is due to two researchers, Jeff Dean and Sanjay Gamawat. Jeff Dean, by the way, is one of the most legendary engineers in all of Silicon Valley, and he kind of built a large fraction of the architecture or the infrastructure that all of Google runs on today. But here's the MapReduce idea. So let's say I have some training set, we'll denote by this box here of XY pairs, right? So X1, Y1, down to my 400 examples, XM, YM. So that's my training set with 400 training examples. In the MapReduce idea, what I'm going to do is split this training set into different subsets. And I'm going to assume for this example that I have 4 computers or 4 machines to run in parallel on my training set, which is why I'm splitting this into 4 machines. If you have 10 machines or 100 machines, then you would split your training set into 10 pieces or 100 pieces or what have you. And what the first of my 4 machines is going to do, say, is use just the first 1/4 of my training set. So we use just the first 100 training examples. And in particular, what it's going to do is look at this summation and compute that summation for just the first 100 training examples. So let me write that out. I'm going to compute a variable temp1, the superscript 1 denotes as the first machine, j equals sum from I equals 1 through 100, and then I'm going to plug in exactly that term there. So I have h theta xi minus yi times xij, right? So that's just that gradient descent term up there. And then similarly, I'm going to take the second quarter of my data and send it to my second machine. And my second machine will use training examples 101 through 200, and compute a similar variable, so the temp2j, which is the same sum but indexed from examples 101 through 200. And similarly, machines 3 and 4 will use the third quarter and the fourth quarter of my training set. So now each machine has to sum over 100 instead of over 400 examples, and so it has to do only a quarter of the work, and thus presumably it could do it about 4 times as fast. Finally, after all these machines have done this work, I'm going to take these temp variables and put them back together. So I'm going to take these variables and send them all to a centralized master server. And what the master server will do is combine these results together. And in particular, it will update my parameters theta j according to theta j gets updated as theta j minus the learning rate alpha times 1 over 400 times temp 1j plus temp 2j plus temp 3j plus temp 4j. And of course we have to do this separately for j equals 0, up to n, where n is the number of features. So sorry about breaking this equation into multiple lines, but I hope it's clear. So what this equation is, what it's doing is exactly the same as that, where you have a centralized master server that takes the results, the temp1j, temp2j, temp3j, temp4j, and adds them up. And so, of course, the sum of these four things, right, that's just the sum of this, plus the sum of this, plus the sum of this, plus the sum of that, and those four things just add up to be equal to this sum that we were originally computing in batch gradient descent. And then we have the alpha times 1 of 400, alpha times 1 of 400, and thus this is exactly equivalent to the batch gradient descent algorithm. Only instead of needing to sum over all 400 training examples on just one machine, we can instead divide up the workload on 4 machines. So here's what the general picture of the MapReduce technique looks like. We have some training sets, and if we want to parallelize across 4 machines, we'll take the training set and split it, equally, or split it as evenly as we can into 4 subsets. Then we're going to take the 4 subsets of the training data and send them to 4 different computers. And each of the 4 computers can compute a summation over just 1/4 of the training set. And then finally, each of the computers takes the results, sends them to a centralized server, which then combines the results together. So on the previous slide, in that example, the bulk of the work in gradient descent was computing the sum from I equals 1 to 400 of something. So more generally, sum from I equals 1 to m of that formula for gradient descent. And now, because each of the 4 computers can do just 1/4 of the work, potentially you can get up to a 4x speedup. In particular, if there were no network latencies and no cost of the network communication to send the data back and forth, you can potentially get up to a 4x speedup. Of course, in practice, because of network latencies, the overhead of combining the results afterwards, and other factors, in practice you get a slightly less than a 4x speedup. But nonetheless, this sort of MapReduce approach does offer us a way to process much larger data sets than is possible using a single computer. If you're thinking of applying MapReduce to some learning algorithm in order to speed this up by parallelizing the computation over different computers, the key question to ask yourself is, can your learning algorithm be expressed as a summation over the training set? And it turns out that many learning algorithms can actually be expressed as computing sums of functions over the training set. And the computational expense of running them on large data sets is because they need to sum over a very large training set. So whenever your learning algorithm can be expressed as a sum over the training set, or whenever the bulk of the work of a learning algorithm can be expressed as a sum of the training set, then MapReduce might be a good candidate for scaling your learning algorithms to very, very big data sets. Let's just look at one more example. Let's say that we want to use one of the advanced optimization algorithms, so things like LBFGS, conjugate gradient, and so on. And let's say we want to train a logistic regression learning algorithm. For that, we need to compute 2 main quantities. One is for the advanced optimization algorithms like LBFGS and conjugate gradient, we need to provide it a routine to compute the cost function of the optimization objective. And so for logistic regression, you remember that the cost function has this sort of sum over the training set again. And so if you're parallelizing over 10 machines, you would split up the training set onto 10 machines and have each of the 10 machines compute the sum of this quantity over just 1/10 of the training data. Then the other thing that the advanced optimization algorithms need is a routine to compute these partial derivative terms. And once again, these derivative terms for logistic regression can be expressed as a sum over the training set. And so once again, similar to our earlier example, you would have each machine compute that summation over just some small fraction of your training data. And finally, having computed all of these things, they could then send their results to a centralized server, which can then add up the the partial sums. This corresponds to adding up those, temp I or the temp ij variables, which were computed locally on machine number I. And so the centralized server can sum these things up and get the overall cost function and get the overall partial derivative term, which you can then pass to the advanced optimization algorithm. So more broadly, by taking other learning algorithms and expressing them in sort of summation form, or by expressing them in terms of computing sums of functions over the training set, you can use the MapReduce technique to parallelize other learning algorithms as well and scale them to very large training sets. Finally, as one last comment, so far I've been discussing MapReduce algorithms as allowing you to parallelize over multiple computers, maybe multiple computers in a computer cluster or over multiple computers in a data center. It turns out that sometimes even if you have just a single computer, MapReduce can also be applicable. In particular, on many single computers now, you can have multiple processing cores. You can have multiple CPUs, and within each CPU, you can have multiple cores. And so if you have a large training set, what you can do if, say, you have a computer with 4 cores, with 4 computing cores, what you can do is even on a single computer, you can split the training set into multiple pieces and send the training set to different cores within a single box, like within a single desktop computer, within a single server, and use MapReduce this way to divvy up the workload. Each of the cores can then carry out the sum over, say, 1/4 of your training set, and then they can take their partial sums and combine them in order to get the summation over the entire training set. The advantage of thinking about MapReduce this way, as parallelizing over cores within a single machine rather than parallelizing across multiple machines, is that this way you don't have to worry about network latency, because all the communication, all the sending of the temp j variables back and forth, all that happens within a single machine. And so network latency becomes much less of an issue compared to if you were using this to parallelize over different computers within a data center. Finally, one last caveat on parallelizing within a multi-core machine. Depending on the details of your implementation, if you have a multi-core machine and if you have certain numerical linear algebra libraries, it turns out that there's some numerical linear algebra libraries that can automatically parallelize their linear algebra operations across multiple cores within the machine. So if you're fortunate enough to be using one of those numerical linear algebra libraries, and certainly this does not apply to every single library, but if you're using one of those libraries and if you have a very good vectorized implementation of a learning algorithm, sometimes you can just implement your standard learning algorithm in a vectorized fashion and not worry about parallelization, and your numerical linear algebra library could take care of some of it for you so that you don't need to implement MapReduce. But for other learning problems, taking advantage of this sort of MapReduce implementation, or using this MapReduce formalism to parallelize across cores explicitly yourself might be a good idea as well, and could let you speed up your learning algorithm. In this video, we talked about the MapReduce approach to parallelizing machine learning by taking your data and spreading them across maybe many computers in the data center. Although these ideas are applicable to parallelizing across multiple cores within a single computer as well. And today there are some good open source implementations of MapReduce. So there are many users of an open source system called Hadoop, and using either your own implementation or using someone else's open source implementation, you can use these ideas to parallelize learning algorithms and get them to run on much larger data sets than is possible using just a single machine. In this and the next few videos, I want to tell you about a machine learning application example, or a machine learning application case study centered around an application called PhotoOCR. There are 3 reasons why I want to do this. First, I wanted to show you an example of how a complex machine learning system can be pulled together. Second, I want to talk about the concept of a machine learning pipeline and how to allocate resources when you're trying to decide what to do next. And this can be either in the context of you working by yourself on a big application, or it can be in the context of a team of developers trying to build a complex application together. And third and finally, the PhotoOCR problem also gives me an excuse to tell you about just a couple more interesting ideas for machine learning. One is some ideas on how to apply machine learning to computer vision problems, and second is the idea of artificial data synthesis, which we'll see in a couple of videos. So let's start by talking about what is the PhotoOCR problem. PhotoOCR stands for Photo Optical Character Recognition. With the growth of digital photography and more recently the growth of cameras in our cell phones, we now have tons of digital pictures that we take all over the place. And one of the things that has interested many developers is how to get our computers to understand the content of these pictures a little bit better. The PhotoOCR problem focuses on how to get computers to read the text that appears in images that we take. Given an image like this, it might be nice if the computer can read the text in this image, so that if you're trying to look for this picture again, you could type in the words, Lulubee's Antique Mall, and have it automatically pull up this picture, so that you're not spending lots of time digging through your photo collection of maybe hundreds or thousands of pictures in order to find this. So the photo OCR problem does exactly this, and it does so in several steps. First, given a picture, it has to look through the image and detect where is there text in the picture. And after it has done that, or if it successfully does that, it then has to look at these text regions and actually read the text in those regions. And hopefully, if it reads it correctly, it'll come up with these transcriptions of what is the text that appears in the image. Whereas OCR, or optical character recognition of scanned documents, is a relatively easier problem, doing OCR from photographs today is still considered a very difficult machine learning problem. And if you can do this, not only can this help our computers to understand the content of our outdoor images better, there are also applications like helping blind people. For example, if you could provide to a blind person a camera that can look at what's in front of them and just tell them what are the words that may be on the street sign in front of them. And there are also researchers today working on photo OCR to help with car navigation systems. For example, imagine if your car could read the street signs and help you navigate to your destination. In order to perform photo OCR, here's what we can do. First, we can go through the image and find the regions where there's text in the image. So shown here is one example of text in the image that a photo OCR system may find. Second, given the rectangle around that text region, we can then do character segmentation, where we might take this text box that says Antique Mall and try to segment it out into the locations of the individual characters. And finally, having segmented out into individual characters, we can then run a classifier which looks at the images of the individual characters and tries to figure out that the first character is an A, the second character is an N, the third character is a T, and so on. So that by doing all that, hopefully you can then figure out that this phrase is Lulubee's Antique Mall, and similarly for some of the other words that appear in that image. I should say that there's some photo OCR systems that do even more complex things, like a bit of spelling correction at the end. So if, for example, your character segmentation and character classification system tells you that it sees the word C1EANING, then a sort of spelling correction system might tell you that this is probably the word cleaning, and your character classification algorithm had just mistaken the L for a 1. But for the purpose of what I want to do in this video, let's ignore this last step and just focus on the system that does these 3 steps of text detection, character segmentation, and character classification. A system like this is what we call a machine learning pipeline. In particular, here's a picture showing the photo OCR pipeline. We have an image which is then fed to the text detection system, and having detected the text regions, we then segment out the characters, the individual characters in the text, and finally we recognize the individual characters. In many complex machine learning systems, these sorts of pipelines are common, where you can have multiple modules, in this example the text detection, character segmentation, character recognition modules, each of which may be a machine learning component, or sometimes it may not be a machine learning component, but to have a set of modules that act one after another on some piece of data in order to produce the output you want, which in the photo OCR example is the final transcription of the text that appeared in the image. If you're designing a machine learning system, one of the most important decisions will often be exactly what is the pipeline that you want to put together. In other words, given the photo OCR problem, how do you break this problem down into a sequence of different modules? And your design of the pipeline and the performance of each of the modules in your pipeline will often have a big impact on the final performance of your overall algorithm. If you have a team of engineers working on a problem like this, it's also very common to have different individuals work on different modules. So I could easily imagine text detection easily being the task of anywhere from 1 to 5 engineers, character segmentation maybe another 1 to 5 engineers, and character recognition being another 1 to 5 engineers. And so having a pipeline like this often offers a natural way to divide up the workload amongst different members of an engineering team as well. Although, of course, all of this work could also be done by just one person if that's how you want to do it. In complex machine learning systems, the idea of a pipeline or of a machine learning pipeline is pretty pervasive. And what you just saw is a specific example of how a photo OCR pipeline might work. In the next few videos, I'll tell you a little bit more about this pipeline, and we'll continue to use this as an example to illustrate, I think, a few more key concepts of machine learning. In the previous video, we talked about the photo OCR pipeline and how that works, in which we would take an image and pass the image through a sequence of machine learning components in order to try to read the text that appears in an image. In this video, I'd like to tell you a bit more about how the individual components of the photo OCR pipeline works. In particular, most of this video will center around a discussion of what's called a sliding windows classifier. The first stage of the photo OCR pipeline was text detection, where we would look at an image like this and try to find the regions of text that appear in this image. Text detection is an unusual problem in computer vision because depending on the length of the text you're trying to find, these rectangles that you're trying to find can have different aspect ratios. So in order to talk about detecting things in images, let's start with a simpler example of pedestrian detection, and we'll then later go back to apply the ideas that were developed in pedestrian detection and apply them to text detection. So in pedestrian detection, you want to take an image that looks like this and find the individual pedestrians that appear in the image. So there's one pedestrian that we found, there's a second one, a third one, a fourth one, a fifth one, and a sixth one. And this problem is maybe slightly simpler than text detection just for the reason that the aspect ratio of most pedestrians are pretty similar, and so we can just use a fixed aspect ratio for these rectangles that we're trying to find. So by aspect ratio, I mean the ratio between the height and the width of these rectangles. So they're all the same for different pedestrians, but for text detection, the height to width ratio is different for different lines of text. Although for pedestrian detection, the pedestrians can be different distances away from the camera, and so the height of these rectangles can be different depending on how far away they are, but the aspect ratio is the same. In order to build a pedestrian detection system, here's how you can go about it. Let's say that we decide to standardize on this sort of aspect ratio, 82 by 36. And we could have chosen some rounded number like 80 by 40 or something, but 82 by 36 seems to work. What we would do is then go out and collect a large training set of positive and negative examples. So here are examples of 82 by 36 image patches that do contain pedestrians, and here are examples of images that do not. On this slide, I've shown 12 positive examples with y equals 1 and 12 negative examples with y equals 0. In a more typical pedestrian detection application, we may have anywhere from 1,000 training examples up to maybe 10,000 training examples, or even more if you can get even larger training sets. And what you can do is then train a neural network or some other learning algorithm to take as input an image patch of dimension 82 by 36 and to classify y and to classify that image patch as either containing a pedestrian or not. So this gives you a way of applying supervised learning in order to take an image patch and determine whether or not a pedestrian appears in that image patch. Now, let's say we get a new image, a test set image like this, and we want to try to find the pedestrians that appear in this image. What we would do is start by taking a rectangular patch of this image, like that shown up here. So that's maybe an 82 by 36 patch of this image. And we'll run that image patch through our classifier to determine whether or not there is a pedestrian in that image patch. And hopefully our classifier will return y equals 0 for that patch since there's no pedestrian. Next, we then take that green rectangle and we slide it over a bit and then run that new image patch through our classifier to decide if there's a pedestrian there. And having done that, we then slide the window further to the right and run that patch through the classifier again. The amount by which you shift the rectangle over each time is a parameter that's sometimes called the step size of the parameter, sometimes also called the stride parameter. And if you step this over 1 pixel at a time, so if you use a step size or a stride of 1, that usually performs best, but is more computationally expensive. And so using a step size of maybe 4 pixels at a time or 8 pixels at a time or some large number of pixels might be more common, since you're then moving the rectangle a little bit more each time. But so using this process, you continue stepping the rectangle over to the right a bit at a time and running each of these patches through the classifier until eventually, as you slide this window over the different locations in the image, first starting with the first row and then with further rows in the image, you would then run all of these different image patches at some step size or at some stride through your classifier. Now, that was a pretty small rectangle that would only detect pedestrians of one specific size. What we do next is then start to look at larger image patches. So now let's take larger image patches like those shown here and run those through the classifier as well. And by the way, when I say take a larger image patch, what I really mean is when you take an image patch like this, what you're really doing is taking that image patch and resizing it down to 82 by 36, say. So take this larger patch and resize it to be a smaller image, and then there's this smaller resized image that is what you would pass through your classifier to try to decide if there's a pedestrian in that patch. And finally, you could do this at even larger scales and run that sliding windows to the end. And after this whole process, hopefully your algorithm will detect what are the pedestrians that appear in this image. So that's how you train a supervised learning classifier and then use a sliding windows classifier or use a sliding windows detector in order to find pedestrians in an image. Let's now return to the text detection example and talk about that stage in our photo OCR pipeline, where our goal is to find the text regions in the image. Similar to pedestrian detection, we can come up with a labeled training set with positive examples and negative examples, with positive examples corresponding to regions where text appears. So instead of trying to detect pedestrians, we're now trying to detect text. And so the positive examples are going to be patches of images where there is text, and negative examples are going to be patches of images where there isn't text. Having trained this classifier, we can now apply it to a new image, maybe to a test set image. So here's the image that we've been using as an example. Now, let's say we run, for this example, I'm going to run a sliding windows classifier at just one fixed scale, just for purpose of illustration, meaning that I'm going to use just one rectangle size. But let's say I run my little sliding windows classifier on lots of little image patches like this, right, over. If I do that, what I end up with is a result like this, where the white regions show where my text detection system thinks it has found text. And so the axes of these two figures are the same. So there's a region up here corresponds to a region up here. And so the fact that this is black up here represents that the classifier does not think it's found any text up there. Whereas the fact that there's a lot of white stuff here, that reflects that the classifier thinks it's found a bunch of text over there on the image. What I've done on this image on the lower left is actually use white to show where the classifier thinks it has found text, and the different shades of gray correspond to the probability that was output by the classifier. So lighter shades of gray. We've seen over and over that one of the most reliable ways to get a high-performance machine learning system is to take a low-bias learning algorithm and to train it on a massive training set. But where do you get so much training data from? Turns out that in machine learning, there's a fascinating idea called artificial data synthesis. This doesn't apply to every single problem, and to apply it to a specific problem often takes some thought and innovation and insight. But if this idea applies to your machine learning problem, it can sometimes be an easy way to get a huge training set to give to your learning algorithm. The idea of artificial data synthesis comprises of two main variations. The first is if we're essentially creating data from whole cloth, just creating new data from scratch. And the second is if we already have a small labeled training set and we somehow amplify that training set or use a small training set to turn that into a larger training set. And in this video, we'll go over both of those ideas. To talk about the artificial data synthesis idea, let's use the character recognition portion of the photo OCR pipeline, where we want to take as input an image and recognize what character it is. If we go out and collect a large label dataset, here's what the dataset would look like. For this particular example, I've chosen a square aspect ratio, so we're taking square image patches, and the goal is to take an image patch and recognize the character in the middle of that image patch. And for the sake of simplicity, I'm going to treat these images as grayscale images rather than color images. It turns out that using color doesn't seem to help that much for this particular problem. So given this image patch, we'd like to recognize that that's a T. Given this image patch, we'd like to recognize that that's an S. Given that image patch, we'd like to recognize that that's an I, and so on. So all of these are examples of raw images. How can we come up with a much larger training set? Modern computers often have a huge font library, and if you use a word processing software, depending on what word processor you use, it might have all of these fonts and many, many more already stored inside. And in fact, if you go to different websites, there are, again, huge free font libraries on the internet where you can download many, many different types of fonts, hundreds or perhaps thousands of different fonts. So if you want more training examples, one thing you can do is just take characters from different fonts and paste these characters against different random backgrounds. So you might take this alphabet C and paste that C against a random background, and if you do that, you now have a training example of an image of the character C. So after some amount of work, it is a little bit of work to synthesize realistic looking data, but after some amount of work, you can get a synthetic training set like that. Every image shown on the right was actually a synthesized image where you take a font from maybe a random font downloaded off the web, and you paste an image of one character or a few characters from that font against a sort of random background image, and then apply maybe little blurring operators, maybe little affine distortions, affine meaning just shearing and scaling and little rotation operations. And if you do that, you get a synthetic training set like the one shown here. And this is work, right? It takes thought and work in order to make the synthetic data look realistic. And if you do a sloppy job in terms of how you create the synthetic data, then it actually won't work well. But if you look at these, the synthetic data actually looks remarkably similar to the raw data. And so by using synthetic data, you have essentially an unlimited supply of training examples for artificial data synthesis. And so if you use this sort of synthetic data, you have essentially an unlimited supply of label data to train a supervised learning algorithm for the character recognition problem. So this is an example of artificial data synthesis where you're basically creating new data from scratch. You're just generating brand new images from scratch. The other main approach to artificial data synthesis is where you take examples that you currently have. So where you take a raw example, maybe from a raw image, and you create additional data so as to amplify your training set. So here's an image of a character A from a raw image, not a synthesized image. And I've overlaid this with the grid lines, just for the purpose of illustration. It shouldn't actually have these grid lines, of course. But what you can do is then take this alphabet A, or take this image, and introduce artificial warpings or artificial distortions into the image, so that you can take the image A and turn that into 16 new examples. So in this way, you can take maybe a small label training set and amplify your training set to sort of suddenly get a lot more examples out of it. Again, in order to do this for a particular application, it does take thought and it does take insight to figure out what are reasonable sets of distortions or what are reasonable ways to amplify or to multiply your training set. And for the specific example of character recognition, introducing these warpings seems like a natural choice, but for a different machine learning application, there may be different distortions that might make more sense. Let me just show one example from a totally different domain of speech recognition. So in speech recognition, let's say you have audio clips and you want to learn from the audio clip to recognize what were the words spoken in that clip. So let's say you have one labeled training example. So let's say you have one labeled training example of someone saying a few specific words. So let's play that audio clip here.
0, 1, 2, 3, 4, 5.
All right, so there's some counting from 0 to 5, and so you want to try to apply a learning algorithm to try to recognize the words said in that. So how can we amplify the data set? Well, one thing we can do is introduce additional audio distortions into the dataset. So here I'm going to add background sounds to simulate a bad cell phone connection. When you hear beeping sounds, that's actually part of the audio track. There's nothing wrong with your speakers. But let me play this now.
0, 1, 2, 3, 4, 5.
Right, so you can listen to that sort of audio clip and recognize the sounds. That seems like another useful training example to have. Here's another example, noisy background.
0, 1, 2, 3, 4, 5.
You have cars driving past, people walking in the background. Here's another one. And so in earlier videos, I've said over and over that when you're developing a machine learning system, one of the most valuable resources is your time as the developer in terms of picking what to work on next. Or if you have a team of developers or a team of engineers working together on a machine learning system, again, one of the most valuable resources is the time of the engineers or the developers working on the system. And what you really want to avoid is if you or your colleagues or your friends spend a lot of time working on some component only to realize after weeks or months of time spent that all that work just doesn't make a huge difference on the performance of the final system. In this video, what I'd like to do is talk about something called ceiling analysis. When you have a team working on a pipeline machine learning system, this can sometimes give you a very strong signal, a very strong guidance on what parts of the pipeline might be the best use of your time to work on. To talk about ceiling analysis, I'm going to keep on using the example of the photo OCR pipeline. And as said earlier, each of these boxes, text detection, character segmentation, character recognition, each of these boxes can have even a small engineering team working on it, or maybe the entire system is just built by you, either way. But the question is, where should you allocate resources? And which of these boxes is most worth your effort trying to improve the performance of? In order to explain the idea of ceiling analysis, I'm going to keep using the example of our photo OCR pipeline. As I mentioned earlier, each of these boxes here, each of these machine learning components could be the work of even a small team of engineers, or maybe it could be the whole system could be built by just one person. But the question is, where should you allocate scarce resources? That is, which of these components, or which one or two, or maybe all three of these components is most worth your time to try to improve the performance of? So here's the idea of ceiling analysis. As in the development process for other machine learning systems as well, in order to make decisions on what to do for developing the system is going to be very helpful to have a single row number evaluation metric for this learning system. So let's say we pick character level accuracy. So given a test set image, what is the fraction of alphabets of characters in the test set image that we recognize correctly? Or you can pick some other single row number evaluation metric if you want, but let's say that for whatever evaluation metric we pick, we get that we find that the overall system currently has 72% accuracy. So in other words, we have some set of test set images, and for each test set images, we run it through text detection, then character segmentation, then character recognition, and we find that on our test set, the overall accuracy of the entire system was 72% on whatever metric you chose. Now, here's the idea behind ceiling analysis, which is that we're going to go to, let's say, the first module of our machine learning pipeline, say text detection. And what we're going to do is we're going to monkey around with the test set. We're going to go to the test set, and for every test example, we're just going to provide it the correct text detection outputs. Right? So in other words, we're going to go to the test set and just manually tell the algorithm where the text is in each of the test examples. So in other words, we're going to simulate what happens if we have a text detection system with 100% accuracy for the purpose of detecting text in an image. And really, the way you do that is pretty simple, right? Instead of letting your learning algorithm detect the text in the images, you would instead go to the images and just manually label what is the location of the text in my test set image, and you would then let these ground truth labels of where is the text be part of your test set, and just use these ground truth labels as what you feed in to the next stage of the pipeline, to the character segmentation pipeline. Okay, so just to say it again, by putting a check mark over here, what I mean is I'm going to go to my test set and just give it the correct answers, give it the correct labels for the text detection part of the pipeline. so that it's as if I have a perfect text detection system on my test set. What we're going to do then is run this data through the rest of the pipeline, through character segmentation and character recognition, and then use the same evaluation metric as before to measure what is the overall accuracy of the entire system. And with perfect text detection, hopefully the performance will go up, and in this example, let's say it goes up 89%. And then we're going to keep going. Next, let's go to the next stage of the pipeline, to character segmentation. So again, I'm going to go to my test set, and now I'm going to give it the correct text detection output and give it the correct character segmentation output. So just go to the test set and manually label the correct segmentations of the text into individual characters and see how much that helps. And let's say it goes up to 90% accuracy for the overall system. Right, so as always, the accuracy is the accuracy of the overall system. So it's whatever the final output of the character recognition system is, whatever the final output of the overall pipeline is, going to measure the accuracy of that. And then finally, I'm going to go to the character recognition system and give that the correct labels as well. And if I do that too, then no surprise, I should get 100% accuracy. Now, the nice thing about having done this analysis is we can now understand what is the potential upside, the upside potential for improving each of these components. So we see that if we get perfect text detection, our performance went up from 72 to 89%. So that's a 17% performance gain. So this means that if we take a current system and we spend a lot of time improving text detection, that means that we could potentially improve our system's performance by 17%. It seems like it's well worth our while. Whereas in contrast, when going from text detection, when we gave it perfect character segmentation, performance went up only by 1%. So that's a more sobering message. It means that no matter how much time you spend on character segmentation, maybe the upside potential is going to be pretty small, and maybe you do not want to have a large team of engineers working on character segmentation if this sort of analysis shows that even when you give it the perfect character segmentations, your performance goes up by only 1%. So that really estimates what is the ceiling or what's an upper bound on how much you can improve the performance of your system by working on one of these components. And then finally, going from character, when we get better character recognition, the performance went up by 10%. So, again, you have to decide, is a 10% improvement, how much is that worth your while? But this tells you that maybe with more effort spent on the last stage of the pipeline, you can improve the system. You can improve the performance of the systems as well. Another way of thinking about this is that by going through this sort of analysis, you're trying to figure out, what is the upside potential of improving each of these components, or how much could you possibly gain if one of these components became absolutely perfect, and this really places an upper bound on the performance of that system. So the idea of ceiling analysis is pretty important. Let me just illustrate this idea again, but with a different example of a more complex one. Let's say that you want to do face recognition from images. So let's say you want to look at the picture and recognize, whether or not the person in this picture is a particular friend of yours, or try to recognize the person shown in this image. This is a slightly artificial example. This isn't actually how face recognition is done in practice, but I want to step through an example of what a pipeline might look like to give you another example of how a ceiling analysis process might look. So we have a camera image, and let's say that we design a pipeline as follows. Let's say the first thing you want to do is do pre-processing of the image. So let's take this image like I have shown on the upper right, and let's say we want to remove the background. So do pre-processing, the background disappears. Next, we want to say detect the face of the person. That's usually done with a learning algorithm. So we'll run a sliding windows classifier to draw a box around the person's face. Having detected the face, it turns out that if you want to recognize people, it turns out that the eyes is a highly useful cue. We actually, in terms of recognizing your friends, the appearance of their eyes is actually one of the most important. Welcome to the final video of this machine learning class. We've been through a lot of different videos together. In this video, I'd like to just quickly summarize the main topics of this class and then say a few words at the end, and that will wrap up the class. So what have we done? In this class, we spent a lot of time talking about supervised learning algorithms like linear regression, logistic regression, neural networks, SVMs, for problems where you have labeled data and labeled examples xi, yi. And we also spent quite a lot of time talking about unsupervised learning algorithms like K-means clustering, principal components analysis for dimensionality reduction, and anomaly detection algorithms for when you have only unlabeled data xi, although anomaly detection can also use some labeled data to evaluate the algorithm. We also spent some time talking about special applications or special topics like recommender systems and large-scale machine learning systems, including parallelized like MapReduce systems, as well as some special applications like sliding windows object classification for computer vision. And finally, we also spent a lot of time talking about different aspects of sort of advice on building a machine learning system. And this involved both trying to understand what is it that makes a machine learning algorithm work or not work. So we talked about things like bias variance and how regularization can help with some variance problems. And we also spent a lot of time talking about this question of how to decide what to work on next, or how to prioritize how you spend your time when you're developing a machine learning system. So we talked about evaluation of learning algorithms, evaluation metrics like precision recall, F1 score, as well as practical aspects of evaluation like the training, cross-validation, and test sets. And we also spend a lot of time talking about debugging learning algorithms and making sure that your learning algorithm is working. So we talked about diagnostics like learning curves, and also talked about things like error analyses and ceiling analyses. And so all of these were different tools for helping you to decide what to do next, or how to spend your valuable time when you're developing a machine learning system. And so in addition to having the tools of machine learning at your disposal, so knowing the tools of machine learning like supervised learning, unsupervised learning, and so on, I hope that you now not only have the tools, but that you know how to apply these tools really well to build powerful machine learning systems. So that's it. Those were the topics of this class, and if you've worked all the way through this course, you should now consider yourself an expert in machine learning. As you know, machine learning is a technology that's having huge impact on the science technology industry, and you're now well qualified to use these tools of machine learning to great effect. I hope that many of you in this class will find ways to use machine learning to build cool systems and cool applications and cool products, and I hope that you find ways to use machine learning not only to make your life better, but maybe someday to use it to make many other people's lives better as well. I also wanted to let you know that this class has been great fun for me to teach, so thank you for that. And before wrapping up, there's just one last thing I want to say, which is that it was maybe not so long ago that I was still a student myself, and even today, I still try to take different courses when I have time to try to learn new things. And so I know how time-consuming it is to learn this stuff. I know that you're probably a busy person with many, many other things going on in your life. And so the fact that you still found the time and took the time to watch these videos, and I know that many of these videos just went on for hours, right? And the fact that many of you took the time to go through the review questions, and that many of you took the time to even work through the programming exercises and these long and complicated programming exercises. I wanted to say thank you for that. And I know that many of you have worked hard on this class, that many of you have put a lot of time into this class, that many of you have put a lot of yourselves into this class. So I hope that you also got a lot out of this class, and I wanted to say thank you very much for having been a student in this class.